Hello, this is Tristan Parker, and I'm doing physics homework reviews for chapter 29 in our textbook. So I'm going to start with exercise 29.6, which reads, a coil 4 centimeters in radius containing 500 turns is placed in a uniform magnetic field that varies with time according to B equals, and it has this big equation there that I have written down here for us. Simplified, I've taken the units out, but that is the equation there. Units originally over here are Teslas per second, and over here are Teslas per second to the fourth. And so it evens out here to give us just Teslas, which is what the magnetic field is measured in. The coil is connected to a 600 ohm resistor, as we see there, and its plane is perpendicular to the magnetic field, so I've lined it up such. So the coil, I drew it as just half a ring. You can imagine the other half making the complete coil. Its plane is perpendicular to the magnetic field. Another way to think about it is you could say the direction of its area is parallel with the magnetic field, since the area would point out in either direction. And we can ignore the resistance of the coil. So part A to the question, find the magnitude of the induced EMF in the coil as a function of time. And so we'll want to keep it as a function of time, and so we conveniently have a function of time here involved, and everything else is constant. And so we use the equation that EMF equals negative the number of turns times the derivative of the flux. So there's our equation, and to simplify it a little bit and make it something we can use, we'll split up the derivative of flux into the derivative of the magnetic field as a function of time and area times the cosine between the direction of the area and the magnetic field which is 0. And so, well, the angle is 0. So cosine of 0 is 1, so we can ignore it. So we have it where the EMF equals our negative 500 times by the area, which is just the radius squared times pi. But first I converted it into meters rather than centimeters, so it's 0.04 meters. So it's negative 500 times that area times the derivative with regards to time of our magnetic field. And so the area we have as a constant, negative 500 turns is constant. And so we just need to find the derivative of our magnetic field, which conveniently we're in terms of time up here already. So we just derived this to be our negative n times a times 0.012 plus 1.2 times 10 to the negative fourth t cubed. And then to find our answer, we just plug in the numbers there, which ends up giving us negative point. Don't need that. So part B is asking what the current in the resistor is at time 5 seconds. And so to do that, we just plug in the equation. We use the equation for, and so to do that, we use the equation for current, which is, well, the EMF equals IR, and I is what we're looking for, so we have I equals our EMF over R. And so our EMF, which we have down here as an equation according to time, over our resistance, which is 600 ohms, since it's allowing us to ignore the resistance of the coil. And so we just plug in 5 for this and solve for that divided by R, which gives us negative 0.0679 amps, or negative 67.9 milliamps. It doesn't ask for direction, so we can ignore the negative. It's just asking for magnitude.